Hey everyone, welcome to my YouTube video. Today we'll be talking about our question number 4 here from our exam, having to do with empirical formulas. So let's get started and jump right into it. I'll first read the problem, the answers, and then give a little bit of a background and then provide the steps to answering this correctly. All right, so here's our question. An experiment was performed that determined the elemental composition of a compound. The results were fluorine 80.8% by mass and carbon 19.2% by mass. Can you find the empirical formula of this compound? Here we have a few options: CF2, C3F8, C2F4, and C3F4. So this problem is asking for the empirical formula of the given compound. The given compound's composition was provided, and it consists of fluorine and carbon. 80.8% of the compound is composed of fluorine by mass, and 19.2% of the compound is made up of carbon based on mass. Let's first identify what an empirical formula is, how to understand what these mass percentages are, and how the two are correlated with one another. Empirical formulas are the simplest ratios of elements in a molecule, also known as the simplest ratio of atoms in a compound. To use a water molecule as an example, H2O is the simplest form already, so we can consider this molecular formula to already be in its empirical form, or simplest ratio. However, if we were to look at the molecular formula of hydrogen peroxide, for example, H2O2, we can find its empirical formula by reducing its atoms while maintaining its ratio. How do we do this exactly? Well, we divide. The lowest common factor between these two elements of hydrogen and oxygen and hydrogen peroxide is 2. We know that we can divide each element by 2 and thus further reduce its molecular formula down to just H1O1. This is the empirical formula of hydrogen peroxide. To give you a better idea of what mass percentages are, since they are given in this problem, mass percentages relate the mass of interest relative to the overall compound, and it's expressed as a percentage. They help us quantify a specific element's amount within a molecule or compound, and they maintain their percentages no matter the size of the sample to keep it consistent. This is why we use percentages instead of grams sometimes. So, in this example, the problem already gives us the composition of the compound, with 80.8% of it as fluorine and 19.2% of the compound as carbon. We gather these calculations based on the mass. However, since we are focusing on just the empirical formula calculation in this scenario, we will go through the steps of how to compute it when given the mass percentages instead of the mass in grams. You can calculate the empirical formula in a few ways, but we will focus on this method given the circumstances of the problem. To calculate the empirical formula when working with mass percentages, we will first always assume that the percentages can be converted into grams when we assume that the sample equals 100 grams. This will maintain the ratio percentages when we compute it mathematically so we can get an accurate answer. So looking back at our given problem, 80.8% is the given percentage of fluorine in this compound. We can convert this measurement into grams by simply keeping the same exact numerical value at 80.8, but just changing the units to grams instead. We will use 80.8 grams in our next step. We will do the same thing for our carbon mass percentage, which is 19.2% of the compound. What will this be in grams when our sample is 100 grams? Well, 19.2% of 100 grams is 19.2 grams. We'll use this numerical value in our calculations. Now that we have properly converted our mass percentages into actual masses given the hypothetical sample of 100 grams, we can move on to the next step. With these given masses, 80.8 grams of fluorine and 19.2 grams of carbon, we will apply our dimensional analysis skills since we have to convert our units from grams into quantity of atoms. Now, can you remember what we can use as a unit to measure our quantity of atoms? That's right. We can use moles in this equation. We can use this as our roadmap as we move forward. Our roadmap is going from a percentage into grams, then into moles. I hope you remember how to set up your dimensional analysis equations because you're going to need it in this. Now, we must always determine our conversion factors when we perform dimensional analysis. Based on our roadmap, we are trying to go from grams into moles, right? We will always start with the measurements that are given to us. We know that fluorine is 80.8 grams and that carbon is 19.2 grams. We will treat these two elements separately as we do our conversions separately so things don't get messy. Let's start with fluorine first, shall we? Here we write out what's given to us, 80.8 grams of fluorine, and we make sure to always label our numerical values with units so we know what we're working with. Plus, it becomes less confusing since it's more organized this way. We then multiply this mass value by our conversion factor of 1 mole fluorine over fluorine's mass, found on the periodic table, which is 19.00 grams. We know that the unit of moles goes into the numerator spot because this is the n unit that we're trying to convert to. We know that for the denominator, we must match the same unit as the given to make sure that they will cancel out. So it must be grams. When we solve this equation, we get 4.2526 moles of fluorine. We repeat the same procedure but for carbon instead so that we can find the ratio of these two elements to each other in moles. For carbon, we will start with a 19.2 grams of carbon and make sure to label it properly. Can you guess what our conversion factor is for this equation? I'll give you a hint. It's a similar setup to the conversion we performed for fluorine that we just did. Since we are following our roadmap of converting grams into moles, we must multiply 19.2 grams of carbon by the conversion factor of moles to grams, as our goal is to end up with an answer in the units of moles. We will look at the periodic table to refer to carbon's mass, which is 12.01 grams, and this is equivalent to 1 mole of carbon. Therefore, we can say that 1 mole of carbon equals 12.01 grams of carbon. Moles will go into the numerator as the units in the denominator, grams, will cancel out the initial given value, or 19.2 grams of carbon in this case. Our equation will look like this. We apply the rule of PEMDAS, or order of operations, where we first solve whatever is in parentheses, then move into exponents, multiplication, division, addition, and last but not least, subtraction. As you can see, we are only performing two functions here, multiplication and division, but we will multiply first, then divide after to maintain our order of operations rules. The answer you should get is 1.5986 moles of carbon. We know that our units are in moles because the denominator of grams is canceled out due to the initial given value also being in grams. Now that we have converted the masses of each element to moles, we can do the next step, which is to divide the moles of each element by the smallest value to find the ratio of the atoms. So we have two values to focus on now. 4.2526 moles of fluorine and 1.5986 moles of carbon. Can you tell me which is the smaller value of these two measurements? You are correct. It's 1.5986 moles of carbon. We will take this value and use it to divide both values. To clarify, we will take fluorine's mole measurement and divide 4.2526 moles fluorine by carbon's measurement of 1.5986 moles of carbon, since it is a smaller value of the two. So we do 4.2526 moles of fluorine divided by 1.5986 moles of carbon, and we get 2.66 moles of fluorine. We will also divide the carbon's measurement by itself since it is the smallest value. So 1.5986 moles of carbon divided by itself, which gives us 1 mole. Now that we have these two values, 2.66 moles of fluorine and 1 mole of carbon, to give us a better idea of our simplest ratio of elements, aka the empirical formula, we have to make sure that we are working with whole integers. This is because we can't use numbers with decimals as subscripts until they are whole numbers, so that it is easier to read and cleaner to write and understand. Remember, we have to maintain the same ratios so that our answer is accurate. In order to do this, we must multiply the value of 2.66 moles of fluorine until we reach a whole number. By multiplying this by 3, we will get 8 moles of fluorine. And to make sure we're also maintaining the ratio, we have to multiply the other element, carbon, by this same number as well. So 1 mole of carbon times 3 is 3 moles of carbon. Now we have found our final answers of 8 moles of fluorine and 3 moles of carbon after applying dimensional analysis, converting our units from grams into moles, and dividing each element by the element with the smallest number of moles. This gives us the empirical formula, or also known as the simplest ratio of elements in a compound. In conclusion, the simplest ratio of atoms in this problem, based on the given mass percentages of fluorine and carbon, is C3F8. We now know how to find our empirical formula when given the mass percentages. As a recap, to make sure you'll remember these steps for next time, let me refresh your memory. We will always assume that we have a 100-gram sample when given mass percentage. We convert each element from grams into moles. We divide the moles of each element by the element with the smallest amount of moles, and then we multiply up the ratios if we need to work with whole numbers or integers. Congratulations, you made it this far and you did a great job following along. You'll be a pro at this in no time after lots of practice. Don't forget to give this video a thumbs up, like it, comment down below, and click that subscribe button.